Hey girls, we're going to talk about chemical bonding, and this is just an introduction to get you started so that we can do some real classwork when you come into class next. So here's the definition of a chemical bond: a mutual electrical attraction between the nuclei and valence electrons of different atoms that binds the atoms together. So valence electrons are going to be our most important electrons, and they're going to determine what type of bond we're talking about. So here are the objectives for the chapter. We want to define a chemical bond. We want to know why most atoms form chemical bonds. Describing ionic and covalent, which these are the two different types of bonds. We're going to explain why most chemical bonding is neither purely ionic nor purely covalent, and then we'll be able to classify the bond type according to electronegativity differences and using the periodic table. We'll be able to use the periodic table to determine most of these. This chapter does involve the electronegativity values, and these are in your textbook on page 161 in the last chapter under the section of electronegativity. So here are two types of chemical bonding, and I put them side by side so we can compare and contrast. Ionic is going to occur between metals and nonmetals. And this goes back to your understanding of the periodic table, that the metals are on the left-hand side of the chart and that the nonmetals are on the right-hand side of the chart. If you are still having trouble with this and where that semi-metal line is, it is now imperative that you understand where the metals are and where the nonmetals are. Cations and anions are generally involved where the cation is positive and the anion is negative, and this has occurred because electrons have been transferred. So we'll have a transfer of electrons. These are very strong bonds, and these substances will have high melting and boiling points. Examples: your favorite sodium chloride, magnesium oxide. We will actually make some magnesium oxide later this year, and all of this will result in what we call an ionic compound. On the other side, we have covalent. This occurs among the nonmetals, this type of bond. So the nonmetals are all on the right-hand side of the table. We're talking carbon, nitrogen, oxygen, sulfur, chlorine, etc. There's a share between the electrons, so they are between the two atoms, so the electrons are not transferred from one atom to another. The share is not necessarily equal. Just like if I said I was going to share some M&Ms with you, even if I had an entire pack, I don't have to give you half of the M&Ms in order to have shared them. I can just give you two, and we still would have shared. So the share doesn't have to be equal. And electronegativity is going to determine how, or to the extent to which those electrons are shared. Here are some examples of covalent compounds. We have water, carbon dioxide, hydrogen peroxide, and glucose. You'll remember glucose from photosynthesis. And so I picked these compounds because you've seen them, most of them. Okay, so what do we get in the end? We don't have an ionic compound, but we end up with a molecule. So water, carbon dioxide, hydrogen peroxide are all molecules, and we will call them molecular substances. So sometimes the book will say, and most books do this, so I don't want to say it's just this book, but most books will use covalent and molecular interchangeably, and that's because both of these refer to a share of electrons. Okay, so ionic bonding results in a transfer of electrons, and I want to show you here, you can see with the red arrow where that valence electron of sodium is, I didn't mean to touch the screen. This valence electron that's in the 3s1 is actually transferred to chlorine. And when it does, a bunch of things happen. Notice that, as we talked about last chapter, when these electrons get moved and it loses that valence electron, it also loses the energy level. And then that electron goes to chlorine. Now, the wonderful thing is that both of these atoms now have 8. 1, 2, 3, 4, 5, 6, 7, 8 electrons. And for chlorine, we have, didn't mean to do that. Go back. We're talking 8 in the valence. 1, 2, 3, 4, 5, 6, 7, 8. So we want to have 8 in the outer ring. And for chlorine, there's that red electron came from sodium. It's been transferred to chloride, so 1, 2, 3, 4, 5, 6, 7, 8. So chlorine has a full outer shell. This is called the octet rule. You will remember it from the reading maybe. And sodium also has 8. In covalent bonding, we have to share in order to make 8, because in this case, if this atom actually dumped its electron all to this one atom, it would not have 8. It would just have 7. So in this case, if they share, we end up with each having 8. So for this atom, 1, 2, 3, 4, 5, 6, 7, 8. And for this atom, 1, 2, 3, 4, 5, 6, 7, 8. So the electrons get to be counted twice. Once for this atom and once for this atom. Okay, so here are a couple of examples of covalent bonding. And when we talk about whether the electrons are being shared equally or not. So when the atoms are different, you're going to have a difference in electronegativity. If you go back and look at the table on page 161, the electronegativity value for oxygen is cited as 3.5, and hydrogen is 2.1. So that means that oxygen, because it has a higher electronegativity value, and it's further right on the periodic table, these electrons in the bond are actually closer to the oxygen than they are to the hydrogen. So this creates a pole. And when we say something is polar, just like there's a north pole and a south pole, or somebody has a polar argument is one where there's a definite affirmative side and a definite negative side, or pro and con. We have a bond here that is mostly negative around the oxygen, because that's where the electrons are being held tightest, and that leaves the hydrogen somewhat positive. So this is positive here and negative here. More on this later. Non-polar covalent means that there's no pole, because equal share of electrons. So here we have H2, and they show you the Bohr model, and then they also show you the electron cloud model. So both of these electrons are shared equally, because this hydrogen is not pulling on that electron any more than this hydrogen is pulling on that electron. So here's the electron cloud kind of overview, where you can see the electrons are evenly distributed, so this would be a nonpolar molecule. But here we might have like HCl, where chlorine is pulling the electrons very tightly to it, but hydrogen doesn't have a lot of electron hanging out over it. So the green indicating negative, and the pink here positive. So this is very negative because most of those electrons are close to that atom, and positive because the electron has not left it, but it's hanging out over here. Here's a comparison of ionic and covalent. So here we actually have, remember, transfer of electrons. So all the electrons, the whole, are transferred to this one atom. And polar covalent, here's polar covalent. The electrons are hanging out more with this atom than they are with this atom. But in nonpolar covalent, you have the electrons being shared equally between the two nuclei. Okay, formation of a covalent bond. So why do elements form covalent bonds, or why do they form bonds at all? But in this instance, we're talking specifically about covalent bonds. And that has to do with the energy. This hydrogen as H2 has lower energy than if it's two separate H's. So here we have, this graph is in every textbook you'll ever read about chemistry, and I know some of you are hoping this is the only one you ever have to read. But here we have energy on the y-axis, and picometers is that's the bond length. So picometer is super, super small, and you could see that when the atoms get way too close together, the energy really drops. It's not very stable there. So there's actually a distance, kind of a peak distance, between the two nuclei when a bond is formed and it's favorable. So the potential energy changes during the formation of the hydrogen-hydrogen bond. So here, at this point, we'll start right here. At this point, the separated hydrogen atoms do not affect each other. And then potential energy, as the electrons get closer together, the potential energy decreases as the atoms are drawn together by attractive forces. Here, the potential energy is at a minimum when attractive forces are balanced by repulsive forces. And then eventually, we come over here where potential energy increases when repulsion between like charges outweighs the attraction between opposite charges, and we end up having a bond. Okay, so I wish I had shown this first maybe. Looking at the periodic table, I want to be very, this is the S, these are S, this is 1S, this is 2S1, and this is 2S2, 3S1, 3S2, and then all of these are P's, except for helium is S2. But we're going to talk about Lewis dot structures. So when you have an atom, so this is random element, could be H, He, B, Li, there is kind of a set pattern as to arranging the valence electrons. So just so you know, kind of here is the S, whoops, going back, whoops, and here are the 3p orbitals. So 2 electrons in the S, and then the 1, 2, 3, 4, 5, 6, and the p orbitals. So how do I know how many electrons are valence? Well, it's a periodic trend. So if you weren't able to count it for the last chapter, let's look at it again. The first column has 1 valence electron. The second column has 2, then 3, then 4, then 5, then 6, then 7, then 8. The only exception is helium up here. Helium does not have 8 valence electrons. It will have 2 to be stable. Variable valence in here, most of them for the transition elements, it's 2, but we're going to really kind of leave them out of this chapter. I know, poor transition elements, but life will be easier for you if we kind of leave them out of this discussion. So here we have the valence electrons, and so we're just putting them in the S. Here, there are 2 in that S, and then lithium is going to be here, and then they kind of start separating around, and we'll talk about this. But here's fluorine with 7 valence electrons, and now they 1, 2, 3, 4, 5, 6, 7. And we will pick that up in class. All right, so that's your basics of chemical bonding. I know this graph that I showed at the end talking about the potential energy is kind of complicated, and we'll talk about it a little bit more. But I look forward to seeing you so that we can start making structures.